Okay, so let's get started. Good afternoon, everyone. Before we begin, I would like to start with the Acknowledgement of Country. We acknowledge the traditional owners of country throughout Australia and recognise their continuing connection to land, waters and culture. We pay our respects to their elders, past, present and emerging. So today is the third day of the IChemE Student Summit, yesterday, today and tomorrow. So today's session will focus on the today part. The MCs for this session are myself, so I'm the Vice President of UNSW SUS. We have Gav, the Vice President of Monash SMUS, and Danny, the Vice President of ARMID ACES. So the theme of today's session is sustainable design. So I'm sure everyone has heard of the term sustainability in your daily lives. Sustainability is a concept which is focused and driven today with its basic objectives to reduce consumption of non-renewable resources, minimize waste, and create healthy, productive environments. So we'll be joined by 4 academics who will discuss their work across sustainable design. First, we have Fabio Silveira from EWB, who will talk about human-centered design. Then we have Professor Stratos from Texas A&M and Professor Reklaitis from Purdue University, who will speak about systems engineering and design optimization. And last but not least, Professor Peter Halley from the University of Queensland will talk about sustainable bioplastics. So we hope you enjoy today's session.
We will start the session with Fabio Silveira. Fabio graduated as a chemical engineer at the University of Sao Paulo, Brazil, and is passionate about education, teaching, and learning. Fabio decided to focus his career on stormwater engineering to help mitigate the impact on nature. He studied a master's degree in natural resources engineering at the University of Canterbury and is now doing a PhD in the same field, looking at the natural stormwater treatment systems to understand the influence of groundwater levels and the bed sediment on the surface water quality. I would now like to call upon Fabio, who will discuss the role of human-centered design in the industry.
Hello, good afternoon, everyone. It's a pleasure to be here presenting. I'm gonna start sharing my screen to load the presentation. Yeah, my name is Fabio, Brazilian, and you guys gonna hear a little bit about me throughout the presentation. So from chemical engineer to humanitarian engineering. Yeah, just a little bit of my background. I graduated as chemical and process engineer in Brazil in 2011. And while I was doing my undergrad, I did a bit of work around 1 year work as volunteer, a wastewater treatment plant inside the university, and 1 year as a junior research in a National Institute of Space Research, very fancy name, was looking at advanced ceramic. Back at the time was very interesting. First contact with research was very, very good. But my career really started when I joined Novartis, pharmaceutical company, as engineer trainee. So for 1 year worked as an engineer trainee at the quality assurance and quality control department, looking at make sure the drugs were very good, and we were trying to extend the shelf life of the drug we were using there. So I was doing a lot of analysis, process analysis, and also stability. Was very interesting. I quite enjoyed, and I also worked for 1 year at the project engineer department. So that was a nice challenge for me because my boss, he was from Germany, and he used to speak only in English to me, even though his Portuguese was better. So that was one of the challenges and working there. I joined the department after like a 3-year project. So I was doing actually checking how the plant was after the project finished. So I was updating the design and drawing of all the companies. So I had to go in front of each equipment and see what was coming in, going out, if everything was in order. It was very interesting to see how it looks on site. So you see a lot of mistakes, a lot of things that should be there and it's not, and a lot of things that was there and shouldn't. So that was quite interesting. So, and after that, I decided to go to New Zealand for um, overseas experience because my English was not up to the standards. And I remember my former boss saying that an engineer without English is not good engineer, whatever, regardless whatever you are. So, and then I came to New Zealand was in 2011 for a 6 months uh, term. So to study English and travel. And 1 month later, I started work as a cook. It was very interesting. Do something different, learn a life skill because I like cooking. But when you work as a cook, it's very different. I'm much more efficient now. And I did use a lot of my chemical engineer expertise, like into cooking, and that was very interesting. And 1 year later, came down to Christchurch to work a little bit rebuilding the city. You guys are aware of the 2011 earthquakes, so the city was very destroyed when I arrived, and I joined a construction company. So we were doing earthquake repair using carbon fiber and epoxy resin. So it was very interesting. Again, chemical engineer did help me a lot because was mainly the bond between the epoxy resin and the concrete. So there was a lot of concrete preparation and the resin mix, the resin reaction curve time. So understand those those process was key, and that did help me to develop and make the process even better. Was interesting work in construction, especially here in Christchurch. It's nice to put energy and time, something that you believe in. Rebuilding a city, it's something very regarding. Yeah, it was good, nice atmosphere. Over here, people were very happy that we were here rebuilding the city. And I think that's the main reason that made me stay here because I was very welcome. So and then a career change happened after working a bit here. I had the need to go somewhere else and do something different. So I went for a 6 months backpack in South America, and I had an insight was the water issue and how people were dealing with water, and that did make me sad. And I decided to come to New Zealand and start a water engineer. Uh, so I applied some jobs and didn't work out. Didn't work out the career or the field that I wanted. So I started doing a master's and I started looking at nitrogen cycle in urban stream. So understand what happened to nitrogen, like the form of nitrogen, how much changed over time along the stream. So it was very interesting to see trace levels compared to what we see in a factory. So we try to make everything more concentrated, while in water is everything very low concentration, got different rates. So that was interesting. And now I'm going a PhD, understand the influence of bed sediment and groundwater levels on the surface water quality of in-channel treatment system. So when it rains, it washes off all pollutants from surface, and that normally goes to drainage or to a stream, and then ends up on rivers and oceans. So the idea is to treat that before it arrives into the river, and that's what I've been working for the last few years. And yeah, and I also start working as teacher assistant at the diploma in humanitarian engineering at the University of Canterbury, where I got in touch with humanitarian engineer and have applied some of my knowledge. I learned a lot with other people. It's a very good knowledge exchange working in humanitarian engineer, and that's what I'm doing here. So, how chemical process engineer applied to humanitarian engineer? Uh, when I when I look, I try to synthesize this in three or four topics. So I think the concept of mass balance inside the community is very important. We chemical engineers, we work a lot with mass balance, reactor, and process, factory, product design, and everything. So what arrives, what leaves to the community, what leaves the community, the byproduct. So that's a very interesting concept that I always look at. And especially I'm from Brazil, a developing country. So and then you see that even better because here there is the residues are very well treated, but most developing countries are not. So you see that the mass balance doesn't work quite well, and food and water production and the disposal. So again, mass balance, but when you see the what the communities need more would be good water and good food and where it comes from and the disposal and quality assurance and quality control to try to maintain the good quality throughout time, regardless what happened. And something that I think only us chemical engineer understand quite well that, which is the limited agent or reagent or reactant in these concepts. So that's something that I always think of. So what would make this stop or what like the most important aspect in whatever concept we're dealing with, and trying to go a little bit deeper on each of those concepts with my vision of humanitarian engineer. Um, so mass balance. So yeah, mass balance. Well, you look about the reactants, products, and byproducts. So what gets in and what leaves the community? I think then when I arrived to the community, the most important aspect for me would be water. This is drink every time, every day. So good water means good food. And when water-related disease outbreaks, it's very bad. It spreads very quickly. So assuring you got good water is very important. So water and food. So I think about the water as a whole. So you got drinking water, wastewater, stormwater, irrigation in a community. So and I try to a lot of people they like, oh, this is the drinking water, wastewater, stormwater, but they are related. They can be reused, and that's very important to treat the drinking water, the wastewater, and understand the availability of those and seasonal changes as well. So we here in New Zealand, in Brazil, we are very lucky. We got good water, but it's available to most of people, but that's not the reality worldwide. Um, and also seasonal change. So in Brazil, we got the dry season in winter, so the availability of water is a bit limited. Summertime it rains a lot, so we've got more water, and depends on your water source that might affect the availability of water, and that's something that we always need to think of. And food waste and animals waste, and it's interesting. It's about my background, so it's culturally in Brazil we don't waste food, so we try to eat and use as much more efficient as we can. So all the food waste we give to animals, and we use waste animals to, as fertilizer and so forth. So to understand those that mass balance is very important for me when I arrived in a community or whatever I'm looking at. And with food, it's interesting to know what can be produced and where. So depends on the climate, the area, and the training of people, the willingness to actually plant something, soil conditions, and so forth. So and food for domestic animals. So a lot of people produce food for animals instead of for people, and they buy food. So It's nice to judge that, do a mass balance, and put on paper if it's worth it or not. And the waste, identify and deal with the waste. So a lot of waste, I don't see a waste as waste. I see as potential to do something else. And I think we were Western civilization. We we should we could use better our resource, especially dealing with water. And I'll talk about about this matter on the following slides. And also the scale, and what scale we're talking about, and what is the limiting region of it. Also, when we talk about food and water source, so is it from the river, from rain, from groundwater? So if you know the water source, we know a bit, uh, better of what to expect about the water quality and what would influence its water quality. So it's from the river. You know that under storm conditions, a lot of pollutants would go there, and if there's animals around, all the animals' waste would go there as well. So we need to be careful about that. Groundwater is another matter. So would be if there is any septic tank around that area. So and then that's something that be needs to be worked out with the community. Yeah, quality and quantity. So that's something that I always think of when I think about water, seasonal availability, and treatment. Does it require any treatment, pre-treatment? Can it be used to wash clothes, wash hands, to drink, to boil? So that's something that for chemical engineers is very core thinking when we arrive to community. Food produced locally or buy from other communities. What can be made locally that is currently purchased or traded? So that's something that I always look when I was traveling. Was very interesting because I'm a plant-based diet and my partner isn't. We were traveling in the middle of in Colombia, Bolivia, in the Andes, and we would go to a restaurant that there was like meat and chicken there, and I was like, we are not like I haven't seen like a chicken like or meat for the last like 5 days traveling. I don't think it's safe to eat that. And it's like, no, she'll be all right. So she got food poisoning. So that's something that might happen, and it's very interesting to encourage and try to eat whatever can produce and find locally, especially like in poor developing communities, and and work that out is it's very regarding because they'll be eating better and understand better their diet and what they can improve it. So and another thing, so this is not sure if it's a lot of chemical engineer and know about soil conditions. My family, they are farmers, so I know a little bit about that. And throughout my engineer course, some tricks to understand better soil conditions. But when we look at the water cycle and the food cycle, they are intrinsically related to soil conditions. So it's it's core for me to understand soil conditions as well. So understand soil condition, food cycles. So acid soil, how to identify. So like it's interesting to use a bit of our knowledge to help poor communities. So there's little tricks that you could do to identify. So if the soil reacts with baking soda, it's acid. If reacts with vinegar, it's alkaline. So there's no magic, and little tricks that might help people understand their soil conditions, and also if there is sufficient drainage and organic matter. So if there is no sufficient drainage, um, it's the water doesn't flow to groundwater, and sometimes the soil is too dry that rains and the water There's only surface water going on, running water or surface runoff, and that doesn't infiltrate, so it wouldn't recharge groundwater. It wouldn't make good condition to plant growth, and that can impact. So if we arrive to a place we can identify those things, that it's very good to help any community. And also irrigation. Um, Due to the seasonal variability, if you work out the quantity and quality of water, you can actually use that for irrigation, for example, and also use of fertilizers for plant growth. So a lot of place they don't have enough of nutrients, so and people they tend to use a synthetic fertilizer you buy, do the mix, and and magic, it works. But do we need it? Like in poor communities, like we have plenty of food waste, we have human waste, animals waste that could be used as organic fertilizer, and that's something that, as chemical engineer, I always try to think of it because I've worked in a wastewater treatment plant, and you see that the solid waste from from a wastewater treatment plant is very nutrient rich if properly mixed with soil and also with good sanitation. It works even better than synthetic and fertilizers. So pro cons. So that's it's up to you to talk to the communities and understand their needs and their willingness to do something different or not. And wastewater use treatment feasibility. So this idea here, uh, I talk about soil conditions because the way we we deal with our waste affects soil conditions. For example, if you have a septic tank and a sinkhole, you it's likely that you might impact the soil around and also the groundwater. So the image here is a concept of um, a biogas generation for householdings, and this is actually a constructed one in Brazil. It's becoming very common in rural areas. So as you can see, so we got like intakes would be the toilet or some animals waste that goes to a gas chamber. So anaerobic digestion happens here, and the gas would go over here. And over here, we've got an outlet, and that the bio slurry, that it's nutrient rich as well. So you can actually use to irrigate, to fertilize soil. And this is, as you can see here, this is a homemade one. So this is 3,000 liters tank upside down. So it goes up and down, depends on the amount of gas it has. Over here, it's a 20 liters water container that uses as a filter. So the gas bubbles into water. So part of the smell stays in the water. It doesn't go out uh, in the line. So and this one fits the house. So we've got a GLP tank. The pressure is very different, so few adjustment needs to be done on the element. But it gives around 3 hours of gas per day for each household. So people, when they have this biogas uh, apparatus going on, they don't need to buy any LPG tank. They've got good fertilizer for the property, so empowers them. They don't need to go outside to buy their things. So when you look at the mass balance, things that they produce, the waste, and generate something that they need. So that's how I think we chemical engineers we should think when we go to a place, but that's the feasibility as well. So Brazil is a very warm country, and the weather is very good for this type of reaction. In New Zealand, that wouldn't be the case because it's a bit cold. So if 10 degrees difference in a micro biological reactor does make a big difference. So, and then you need to judge what the community willingness to do that, and if it's feasible as well. And also quality assurance and quality control. So I think it's very, I think the COVID pandemic brought to us the sanitation standards, and that's something that we need to talk about with communities, because these sanitation standards is different worldwide, and more we talk, the better it is. Would be about the water aspects, the food aspects, and also what they use for uh, to irrigate or fertilize the soil, if it's that's hygienic as well, um, pesticides and other things. So I think that englobes very wide range, but it's something that definitely is our job to look at and talk about it. And all, yeah. So when we talk about QA QC, which is the best process for drinking water, they scale limited reagent and trained people. So to do short term, mid term, long term. So that's something that we need to think. And there's a wide range of different techniques that you can perform. So it would be up to us to judge. So this one, it's a UV light technique that kills up to 99% of the germs exposed around 24 hours. Boiling water. This is a chlorine tank, chlorination tank, and this is very common back home in Brazil. It's a classic ceramic filter, so it uses gravity to filter, so it's very slow. But because it's ceramic, the water maintains fresh, and it's very good to drink, regardless the outside temperature. And also food preparation preservation. That's very interesting because a lot of people they leave food unattended, dry into the sun, and you've got flies, you've got worms, you've got a lot of things. So how gonna prepare and preserve food with minimal sanitation standards? So I think as chemical engineers, we can actually talk about it and explain this to the people. And the last one would be feasibility of production. And when it's very good to empower people to produce something, to do something that might generate profit, or even avoid to go to buy from a source outside the community. One thing that I think it's important, that my grandma used to do like 30, 40 years ago, and was soap. So it's very simple to do. You've got you need animal fat, sodium hydroxide, a big pot to actually make the reaction happens. And that's just one example that you can use byproducts, things that would normally go to waste, and to make something that the community might use it and maybe generate profit of it. And that's something that we need to think, and that's also a thing of little bit of mass balance of QA/QC, understand the flux of goods inside there, and
into water and community-based engineering. There are a few questions from the audience that I believe we can cover. So the question from Samson. Was it securing your first bit of work experience?
Say again?
How did you go about showing the initiative for your first construction job overseas in New Zealand?
It was interesting because at the time I didn't have a work permit, a work visa, so I was tourist at the time. So actually knocking companies' door and asking for a job, saying I'm an engineer, I'm looking for a job, I'm up to anything. And this company actually hired me because I hold an engineer degree, and yeah, was challenging because most of the working tools I've never used before. But once you understand the technique, it's good. Yeah, was very regarding helping rebuilding the city.
I agree with that. There's a question from Azriel. It is so important to make sure that you're introducing the community to planning discussions. Have you found any key techniques for bringing your experiences and knowledge to these human-centered designs?
I think uh, a lot of people think the knowledge goes only one way, but the community, they have a lot of knowledge to share as well, mainly practical knowledge. And I think it's very good for us to listen, to understand how they live, what they do. And once we understand that, we can help with the knowledge we have. But they have a lot of knowledge, and they talk, they discuss, and they're willing to learn, but it needs to be reciprocal, not that we are the experts, we go there and we sort all their lives. That's a big lie. And we need to empower them to actually do themselves. And and I think listening and observing them is the key. Once you listen and observe them, and then you can go step by step to actually make good improvement.
That's right. I agree with you. Another question from Ashwin. What are some of the challenges you faced during your career change, and how did you tackle them? Could you have done something different now that you have done differently, now that you're looking back?
Yeah, well, challenge changes throughout. All the challenges I've faced have changed throughout my career. Back in Brazil, the challenge was to actually be the best. It's very competitive over there, and it's very hard to work as engineer there, because if you're not the best, you can be fired, and they gonna get someone pay a bit less or whatever. But it's very competitive there, and I think New Zealand market's a bit different. I think when I arrived to New Zealand, my biggest challenge has been English. Yeah, even like 9 years later, I still struggle, especially writing my PhD thesis at the moment. And I think I've got more since I arrived in New Zealand. I've got more flexibility to try to do what I love instead of whatever comes up to me. And that's why I decided to go to this specific field of stormwater engineer, something that I love, something that I'm willing to spend my time and energy to work and help communities. I work with Christchurch City Council, Environment Canterbury, and I see the result of my work around, and I think that's what the reason that I wake up and I'm happy about what I'm doing.
That's great. Thank you, Fabio.
Hi everyone, we're graced here with two professors in process systems engineering, Professor Reklaitis and Professor Stratos Pistikopoulos. And it's going to be a panel discussion on process systems engineering and how it can be applied to chemical engineering. Professor Reklaitis, do you want to introduce yourself to the audience?
Sure. I'm a faculty member in chemical engineering at Purdue University, which is a engineering, science, agriculture university located in the state of Indiana, about 100 miles south of Chicago. My area is process systems engineering and has been for quite some time. In the course of exploring this field, I've really worked in applications that really go across much of what constitutes chemical engineering.
Yep. And Professor Stratos Pistikopoulos, would you like to introduce yourself to the audience?
Yes, thank you, Danny. It's great to be with all of you. My name is Stratos Pistikopoulos, obviously of Greek origins, as you might have guessed. I'm a professor of chemical engineering at Texas A&M University, which is located approximately 100 miles northwest from Houston, sort of in the triangle between Houston, Dallas, and Austin, which is the capital of Texas. And I'm also the director of the Texas A&M Energy Institute. I have been, in the field of chemical engineering and process systems engineering for the last almost 30 years. So it's great to be here, and actually great to be with Professor Reklaitis, one of the, if you wish, the founders of process systems engineering.
Thanks. Now to get to the first question, for those in the audience unaware or not well versed in the specialization, what is process systems engineering?
Well, there are long definitions and short definitions. The shortest one that I have ever come up with, I have to credit to a colleague, Professor Stefanopoulos, who basically proposed that it's the engineering of systems involving physical, chemical, and biological processing operations. So that's about as succinct as you can make it. And then, of course, you have to go into details of what do you mean by the engineering and what do you mean by systems. And, of course, the importance of the word systems is that the focus is on the big picture, on the integration of elements rather than the reductionist approach of looking at each of the individual elements separately. So the key is, as you think of a process flow sheet, not worrying about the individual pieces, but how do all of these pieces play together? So that's the importance of the systems view. The engineering part, of course, are all of the engineering decisions required in order to design, control, operate a system. So that's the shortest definition I can give you, but we can give you one that goes on for, a long time. And I'll leave the longer version to Professor Pistikopoulos.
Well, I think Rex covered this beautifully. I just add, the medium, like for translating the description of this systems-wide holistic approach, the typical medium that process systems engineering has brought into the picture and is some description of the physics, the chemistry, the underlying phenomena through some type of modeling. So modeling, either being from first principles of data and hybrid of this, constitutes one of the core competencies of process systems engineering. And then instead of performing real experiments on real systems, the realm of process systems engineering is really to develop computational experiments on computational tools. And that has been a core key contribution to process systems engineering, to chemical engineering and beyond, to the systems community.
Pretty much sums it up quite nicely there. Just to follow through, what are the methods of optimization in process systems engineering?
Well, as Professor Pistikopoulos pointed out, the key tool in process systems engineering is the model. And it is the model that dictates what kind of optimization tools you require. And so you can think of, in your design courses, you probably used a steady state process simulator like Aspen Plus or something. So that's the model. If you want to optimize that flow sheet, you first of all have to decide what is it that you mean by optimize. So what's the performance metric? Is it cost? Is it, size, some metric? And then having the metric and the model, you then choose the optimization tools that allow you to find the values of the independent variables that give you the best value of this performance metric that you chose. And so it's really the metric and the model that dictates, what tools you need. Is it going to be, a collection of black box models? So you use simple tools. Is it going to be detailed dynamic models? So you'll need much more sophisticated tools. Are you going to be handling all variables being continuous? Or are some of the variables going to be discrete or integer valued? Depending upon the model, the independent variables, and the performance metrics, there's a whole portfolio of optimization methods that are available. You really have to get into the details in order to be more specific.
Yep. So how would the methods of optimization differ between a continuous process and say a batch process?
Well, normally the inherent difference between a continuous and a batch process is the batch process is inherently dynamic.
Yep.
So if you're going to do anything with it, you automatically have to deal with dynamic models. And so numerically, you have some work to do. One of the advantages of the continuous state, at least for the design point of view, is that we can make do with steady state models, hopefully algebraic models.
And we need to follow, if I can add here, you need one needs to follow also the developments of the process simulation field, because a key contribution of process systems engineering to the profession, which has become an enabler for many of the applications and many of the great things that process systems engineering has done, is the simulation kernel for different classes of problems and the developments of this all the way to commercial tools that educators can use, practitioners can use, the community can use. So optimization, and then you can see steady state simulation has become, like a tool that everybody is aware of and been taught. Dynamic simulation now, the type, for instance, that you have in a batch processor, where you have transient plays a role. When you switch operation, let's say you have like an air separation system, you change products and so forth. Dynamic simulation is becoming a tool again available to most people these days. So therefore, optimization also follows the developments of simulation. So now steady state optimization, as Professor Reklaitis highlighted, is it's a toolkit that everybody is using. Now, as we go into more involved classes of problems, then it becomes a little bit more bespoke kind of type of applications. But we are reaching now a stage where optimization of any form is becoming also standard for most process engineers.
Okay. Professor Reklaitis, as someone who had a big focus in the pharmaceutical industry, what were some of the problems that came up optimizing batch processes for the pharmaceutical industry?
Well, you're correct in that the pharmaceutical industry is very much wedded to batch processing, although in the last half dozen years, there's actually been a strong push to convert these batch processes to continuous, and that is continuing. It started with the conventional solid oral dosage products into the chemical side, and now increasingly into the biologic products as well. So the biggest difficulty in applying PSC tools to pharmaceutical manufacturing has been the fact that you have to capture the process in dynamic models. But fortunately, there have been important developments. For example, the efforts of PSC enterprises and GPROMs to really build tools that allow you to construct these dynamic models in a reasonably efficient way. And of course, not only to allow you to build these models, but also to do the essential parameter estimation that's required in order to tune these models to your specific process. And then, of course, the next step also then to do optimization. So definitely the capability to build models effectively is really key. And I think there will continue to be efforts in this area because, once we get to biologic systems, the modeling problems become much more difficult.
So what's the process for actually optimizing a process through process systems engineering? How do you tackle it from the start?
Can I take this? I can give you two concrete examples of ongoing efforts, which are two different classes of models and two different classes of optimization. So one is a project we're working on air separation systems. Air separation systems, effectively you take air, free, if you wish, and you want to manipulate the molecules by through energy, to get nitrogen out of the way, either gaseous or liquid form, to get oxygen in gaseous or liquid form, and other more valuable like argon and others, right? So effectively, it's a refrigeration system. You beat the physics, right? So it's a multi-product system. It's a continuous, it's a multi-product system that swings its operation so as to be able to deliver all these products, right? Because it's like a utility system, you can view this, right? So how you optimize such a system, which is very complex. So you need to build very detailed mathematical models because because of the refrigeration and the difficulty to separate, to make liquid and nitrogen and so forth, these cryogenic conditions require special attention in terms of modeling. So you build high fidelity models, you synchronize with data that you get from the system, and then you need some type of a dynamic model that also, so dynamic optimization, in other words, an optimization model that has differential and algebraic equations is the right type of medium for this type of process. Special care from a modeling point of view is the physical properties, because obviously if you don't have the right property prediction for for nitrogen, oxygen, and so forth, you cannot really do justice to the system itself. So that's one class of very big, dynamic optimization is one class of optimization. So if you take now another real example, like for instance, a production of hydrogen through a renewable system where you're trying to optimize the supply chain through, let's say, some type of dense energy carriers, let's say methanol or ammonia or hydrogen itself, right? So how you optimize such a system? Now here, the optimization needs to take care of the fact that you have multiple systems working together there, and you have decisions where to place the system. Should I place them in Texas, where the sun is shining and the wind is blowing, or in New York, upstate New York, where there is no sun and and the wind is no, so you have this type of discrete decision. You have a large scale system. So here, to make the long story short, and we can come back to this you need another medium, which is a mixed integer optimization type of model. Typically, you would like to have it as linear because of the large scale. So you get an approximation first on a linear form, you solve this type of problems, and then you zoom in, zoom out, so to validate the model. So that gives you two, let's say, extreme points of reference for the use of optimization models in actual chemical engineering, energy systems, and other sectors like health systems and so forth.
Well, if I could just add to it, I think the important, and I think it's the examples are very illustrative. In order to do optimization, we optimize on the model. It is unsafe and impractical to actually optimize by trial and error on a physical facility. So the key effort is build a model that's sufficiently representative of the real system so that when you determine the optimal solution, there's a reasonable chance that that solution actually will be optimal for the real plant. And so this is really the kind of effort that's always involved. Build a model, make sure it represents the system, optimize the model, implement it on the system to confirm that it actually is a good solution. That's really the classical approach in PSCs.
Are there any really good real-life examples of how this process has been applied?
Oh, very definitely. It's it is routinely used in the chemical and petrochemical industry, both for design and to really optimize operations. So really, there's hardly a petrochemical complex, for example, that doesn't do real-time optimization of the plant set points periodically. It's very, very regular and normal, really.
And we should also add here and also reflect that when people talk about controlling a system, so the implementation of some optimal strategy again involves some type of optimization function to the system, right? So you might want to achieve the targets that you do like through offline optimization, but then to achieve them online, in real systems, in real time, you need to perform some type of control action. So to synchronize, to close the loop kind of, right? So that's again, another optimization function. So those systems now, as Professor Reklaitis mentioned earlier, now there are commercial tools that are becoming available and used, by thousands of companies where are empowered by tools that have been developed by the process systems engineering community in different forms, at different time instances, and as a function of time.
Yeah. No, I think that's really a source of, I think it can be a source of pride for the process systems engineering research community that, there are tools now routinely used that really started as research activities. So steady state flow sheet models, it wasn't that long ago, by my age, where there was significant amount of research. How do we actually build such systems? How should they actually be executing? Similarly, on dynamic simulation, how do we build these things? How do we make it feasible for engineers to really put together realistic models? And the model predictive control, likewise, there's been several decades of research. How do you build these models? How do you effectively use them? How do you tune them to real plant? I mean, these are real, significant accomplishments of the control community. I could add to that also the process integration or process synthesis. I'm sure in your design courses, you looked at the problem of heat exchanger network design, of power systems integration. All of the methodologies for doing that are really the research products of faculty, industrial engineers, and graduate students working in process systems engineering. So it's really been a community that's been productive and has developed tools that are now in the field used routinely.
A a lot of these systems that are optimized have subsystems. How are the complexities of the overall system managed when optimizing a process, that is? Sorry.
I can take this, Rex, if you want. I mean, this is pretty much the art and science of process systems engineering, right? Because we're talking about entire systems, so that we advocate that we need to take the holistic approach, looking at the big picture first, but we should not forget the individual components. So we need to zoom in, zoom out. So how we do this? So modeling is the key. So we built mathematical models at different scales. So it is what we now contemporary term as multi-scale systems engineering. The ability, the way we build the models, they have the capability that we can zoom them up, so we aggregate them through techniques which are becoming available, like surrogate models and so forth. And we can zoom in so that we can build even models at the atomistic level. We don't want to carry all the complexity all of the time at all the levels. So the art and science is how you aggregate and disaggregate these models in a way like the orchestra operates, so that you don't lose control and you don't lose accuracy, and but you gain computational efficiency, and that's how you solve larger scale systems through simulation and optimization.
Well, probably within the scope of the courses that you've had, I'm assuming that you will have, before you graduate, a process design course and a process control course.
Yep.
And in the process design course, you principally focus on, all right, what should be the dimensions of the pieces of equipment and the operating conditions. But I'm sure your instructor said you can't really design a process without thinking about the control implications. And so in your control course, you probably talked about something like the relative gain array, some way of characterizing the gross dynamics of the process. So one simple example of how you put those together is actually include the relative gain type analysis within the scope of the design optimization. And so you can bring, those are really, when you think about it, two different timescale activities: control timescale and design timescales. So you guys are doing that sort of thing. You may not have actually been told explicitly you're really doing multi-scale optimization and design, right?
And the other thing is the role of approximate modeling. We do a lot implicitly and explicitly. For instance, we're using physical properties, right? Equations of states. What are equations of states? Are really model approximations, because we don't want to describe everything from atomistic molecular dynamics. We aggregate them through some expressions that express this behavior without having to rely on very complex atomistic type of computations. You have a design method on distillation column. There you use all kinds of approximations as well. So I think one of the current trends in process systems engineering is to do this in a much more, if you will, systematic way. They're all how you approximate models, so how you zoom in, zoom out, when you build put all these building blocks together. And that has become a core activity in process systems engineering at the moment.
That's interesting, yeah. Knowing that I've been learning it implicitly, I guess you could say. Now to another question. Process systems engineering is largely interdisciplinary field. Which other disciplines are involved to help address the broad and dynamic problems encountered in the field?
Well, I guess what I should start with by saying that actually, from our perspective, process systems engineering is really a core part of chemical engineering. So it is chemical engineering, in total substance. And However, like everything else in science and engineering, we draw on help from lots of different areas. So, for example, if we're working on designing a biological process, we clearly want to draw on the expertise of people in the biological sciences so that we can make the kinds of modeling decisions that Professor Pistikopoulos referred to. What level of detail do we have to put in there to actually capture the process? So we need the domain expertise for building models. We also need the tools. So we need to have the capability of managing data. We have to have numerical methods. All of those rely on, people from mathematics, statistics, computer science. So we do draw on other disciplines for tools. We draw on other disciplines for domain expertise for building models. So the right skill set that we'll need will very much depend on the application. So, for example, I'm currently working in the pharma domain. We collaborate quite a bit with people in pharmaceutical sciences so that we capture what is essential in the kind of models that we build for our manufacturing systems.
And I would like to echo what Professor Reklaitis said on two fronts. One, first of all, that process systems engineering is really at the heart of chemical engineering because it provides the glue between the various components of chemical engineering, right? And then we have like core competencies, like mathematical modeling, like it's a core, right? Like process design, process synthesis, process control, scheduling and operation management. And then we have like more interdisciplinary, we move out, right? Because this systems thinking can provide, as I said, the glue so that we connect, for instance, materials with processes. So think of colleagues, and many in chemical engineering, they spend all their lives on the design of materials, right? Without properly thinking about where this material is going to be used in a process, right? Think of adsorbents and other type of materials in separation system. So by building models of the material and the process itself, you take now a holistic approach. So you provide the computational experimentation form also to help experimentalist colleagues to answer the fundamental question, will that material work in a particular processing system? So that's the realm where systems engineering can open up into a multidisciplinary type of approach.
Well, and I could, in the current context, one of the tool areas that have become very much into the forefront is really data analytics. I'm sure you've heard lots about big data and all that sort of thing. In order to deal with lots of data, we need tools. And some of these tools are generated by people in AI and applied statistics and so forth. The systems community brings them in, and now we apply them to processes. So and of course, in the course of using these tools, invariably, people working in this area will now improve these tools and feed them back to the larger community. And that's really happened over and over again in PSE. Professor Pistikopoulos mentioned mixed integer linear programming type problems. Certainly, I would say mixed integer nonlinear programming, much of the development for the field at large has occurred by key members of the process systems engineering community. So there's usually give back, right? It isn't just taking, you also give back.
Yes, and there are many examples. So there are, we're borrowing many ideas, but we are also, the process systems engineering community is a key developer of many of those tools. So it's not only software development, it's not integration, but it's also development of fundamental knowledge to tame the complexity of those systems and then developing appropriate tools to further expand the field. Yep. And it's interesting to see also, you're talking about, Danny, about, opening up with other disciplines. So it's interesting to see that now process systems engineering, or the systems engineering, this holistic, thinking about the big picture, becomes more and more important in the current environment, because think about energy systems or the future energy systems. I mean, the whole energy, the energy space is being redefined. And that's where systems thinking and the very practices, tools, analysis, modeling that we're doing in process systems engineering can be applied to this type of systems. We talked about life sciences engineering, system, like healthcare systems engineering, like where now we are witnessing an explosion of going back and, thinking about the molecule design of new molecules as drugs, but all the way to the production. Now, this was unheard. And the premium to do this, to the connectivity, the glue, it's not only, it's an interdisciplinary program, but it's also attributed to developments in the process systems engineering. We're talking about the circular economy, sustainability, all this. Again, it's a holistic program, like how you trade off, how you create win-win scenarios for a circular economy, for the fact, we have created all these plastics. What the hell are we going to do with them, right? So all closing the loop is a systems problem, right? So where we can start posing it through the same tools, the same thinking, and the same analysis that process systems engineering has been developing over the last 50 years.
In the current climate, which industry sectors do you feel have the greatest potential for optimization?
Well, there's really a number of them, as was just mentioned. The energy domain is clearly one, because certainly the obvious situation we're seeing with use of renewable sources, which are intermittent, and merging those with existing energy system, with storage systems, so you can deliver power and fuels on a consistent basis. And that's a beautiful large-scale systems area, and lots of chemical engineers working in this domain. Obviously, personally, I feel the healthcare domain is really a huge opportunity. I think if you just look at what's happening now with COVID-19 vaccines, there's lots of discovery, but guess an equal amount of activity on, all right, we'll discover this vaccine, but how do we deliver billions of doses to the world in a reasonable time period? So there's lots of scrambling on how do we put together manufacturing systems that can do this effectively. And that has an implication on the way the product is even, or the vaccine is even developed. It's pretty obvious we no longer can go to the old egg-based way of making vaccines. I'm sure you've read that, one of the current ways we're trying to get away from is using thousands and thousands of eggs as little individual bioreactors where you infect and produce, the antibodies. So we're now going to biological systems that are, cell-based, that can really be scaled up and carried out around the world. So it's really a very exciting time, and we're seeing it happening right now. And there's a lot of concerns about how do we make medicines affordable? How do we go from discovery to the patient and as quickly as possible? So these are the healthcare area in the current climate has really been brought into the forefront, because it's now obvious that healthcare is a global issue.
And I think just to further expand on Professor Reklaitis' comments, because one of the power of process systems engineering thinking and tools and all this kind of analysis is the ability to predict, to do on a computational platform scenario analysis, like what if analysis, right? And not only with the means only to accelerate the cycle time of development, but also to guide proper decision making, not only to select necessarily the best, but also the routes that should be avoided, so very often like managing the risk, the expectations, right? So if you have to invest $100 on some specific new energy route or a new pharmaceutical route, it's not only important to know which ones are going to be winners, but also which ones are going to be definitely losers, right? Because that screening out also possibilities is one of the big, like the designing the envelope of possible solution is important. So, so we accelerate process systems engineers, accelerate not only the cycle time of development, but also enable to do predictive computational experiments like this scenario analysis for improved decision making under risk and uncertainty.
Yeah, this aspect of quantitative assessment of risk is really a very important area for process systems engineering going forward, because investment is always a risk-based decision. Healthcare, invariably, you're trading off, the negative effects of a drug against the positive effects, because, invariably there are always some negative effects in any medicine that you introduce to the body. So I think this general area of quantitative risk management is really, I think, a big area for the future, and already significant work happening.
Professor Pistikopoulos, being in Texas, arguably, or it is the most energy dense state in the United States, how has the presence or the options of alternative energy systems come into the outlook of of the energy demands of Texas?
It's an excellent point, and I think so Texas has been blessed over the years with a lot of natural resources, with oil and gas, and actually one of the big agenda for the future of Texas is clearly how it will take advantage of renewables and other sources of energy, because water management is also key, because we're running out of water at a higher rate than we're running out of oil. So despite the all the shale gas and shale oil, so Texas, it's interesting, if you look carefully, is the #1 state in the US and #2 in the world when it comes to wind energy. If you look at the electricity production in Texas, 17.5% of electricity in Texas is produced from wind. So therefore, the state has been investing heavily on renewables when it comes to wind. Now, solar is interesting. There is a boost for solar. It's mostly on places like California. Now, economics dictate the use of solar and the further development, because solar is a little bit more expensive than wind, and the cost of electricity, for instance, in Texas is so low. So, the solar is not the preferred, but it's really coming up as well. So there is a big change of mind towards solar and wind as renewables. Now, the big picture, however, is we cannot, as Professor Reklaitis alluded to, we cannot solve all our problems with wind and solar, because we create more in our attempt to solve. So we need some other media for going towards other directions, because for transportation, fuels, for chemicals, and so forth. So now here you need to look at what the big oil and gas industries are doing, right? What are the futuristic scenarios? So let me give you 2 examples. So to answer your question directly, and then Professor Reklaitis can talk about other places, trends in the energy sector. So if you look, for instance, in companies like Shell and even some of the Gulf Coast, they have put a lot of their bets on the hydrogen economy.
Yeah.
By hydrogen economy, here we mean they are not going to go directly to hydrogen through renewables, but we can go through intermediates, so the so-called dense energy carriers, like methanol. Ammonia is a big player, or is becoming a big player. We saw the announcement between Aramco and Air Products for a big production of ammonia for hydrogen production in actually Saudi Arabia. So this is a big direction that will shape the energy sector. We see also other companies investing on biofuels, or a combination of this. In other words, how we go from more natural carbon neutral resources to mimicking the biorefinery, the whole economy that we have in terms of transportation, fuels, and other chemicals. We need carbon atoms, we need electricity, we need somehow to manipulate this. So I think Texas is well positioned because it's blessed with wind and solar. So there is an area in the northwest part of Texas where the wind is always blowing and the sun is always shining. So, you can imagine you can build there big investments about wind farms and solar farms, produce their commodities like methanol, ammonia, and then transport them if you go for a centralized scenarios. Professor Reklaitis at Purdue, they do a lot of research on decentralized scenarios that perhaps Rex can talk about, like other means, that can shape the energy, the future of energy.
Well, yeah, no, I can speak for an interesting project that my colleague, Professor Agrawal, has been following developing the last few years, which was really to try to look at a decentralized system that could help farmers. He recognized that solar is really a very plentiful and useful resource around the world. However, it requires land, and that land often is dedicated to agriculture. So the question was, how can you combine that? How can you allow the farmer to grow his crops, generate solar electricity so he can run his pumps and other devices, and do this in an economic fashion? And in fact, they now have a farm near campus where they exactly do that. And from an engineering point of view, the really interesting idea is that you use part of the solar spectrum to generate electricity and part of the solar spectrum to actually continue to grow the crops. And just for good measure, they also threw in a wind turbine just to be ecumenical about the use of technology.
Yeah. And another dimension, perhaps just to close the loop here, is, like natural gas. There is a lot of natural gas around. So we as chemical engineers in the industry has to think second and third, like a lot about potential use of natural gas, because natural gas is going to stay with us for the next 100 years. So natural gas utilization is key also. So we should not, and how we build transition scenarios from fossil fuels to intermediate, to hybrid, all the way to renewables, is going to be something that is going to stay with us. And it's a beautiful chemical engineering problem. So young minds, that all of you can look into it, as we progress.
What role would natural gas play in providing hydrogen if hydrogen was, say, a renewable source? So producing hydrogen from natural gas to supplement a lack of supply in hydrogen in some areas.
Yeah. The beauty of natural gas is, that you can go to any route that you would like to. You can produce hydrogen, you can go gas to liquid, so you can manipulate. The question is how you do this in not only from an economic point of view, but also from a sustainability point of view. Clearly, natural gas is one route to hydrogen, and a lot of, through the reforming, so one way to recover hydrogen is through this type of technologies, right? And so therefore, the key is we need to go back to the fundamentals. We need, as I said, carbon atoms and how you manipulate them effectively. And then we need to think about electrons and how we manipulate the electrons, right? So if you put the carbon, so if I have the carbon atoms and I have my electrons and I manipulate them, I can go to anything through any route, right? So the thing is to do this in an economically feasible way, optimal ideally, and in a sustainable way, right? And so natural gas, I would expect, and it's already playing a big role, and it's going to be playing pivotal role as we move forward in tandem and in conjunction with the renewables and anything else.
Yeah, exactly.
Yeah, I think just to add to that a little bit, I think it's often overlooked in the general community that changing the energy infrastructure is not something that can happen in 1 or 2 or 3 years. If you think of the electric power grids, the pipelines for gas and oil, these are infrastructures that have been built over decades and even centuries. And so we have to think of, a transition from a current state that will systematically build and take us to a future where, all of our energy needs will be renewable, and maybe all of the carbon that we extract will really be used for products that require the carbon rather than as fuels and, creation of CO2. So I think it's very important to think of this transition as something that has going to happen during your careers, because it's really only starting now.
Yes. That's a very important message. How we manage the transition of the energy systems of the future is an unresolved problem that clever minds, young minds need to get into. And, chemical engineers are well positioned to resolve this problem.
Well, there we go. There's a lot of potential research that's forthcoming for all of us. I think we should wrap up here. We could probably go in circles about process systems engineering, I imagine. Thanks. It was really good having you two discuss it. I think that's it. It's been thank you for coming on the webinar series.
Well, certainly is a pleasure to participate in your summit, and hopefully we energize at least some of your community to think of process systems engineering, because I think we need people in this community to do the design and the operation of processing systems to the future. So
yeah, and I would like to echo this. Thank you for inviting us. Continued success, and I think process systems engineering is a wonderful field, and there is already a big representation of excellent process systems engineers in Australia that I'm sure you will all be learning from them. So wish you all the best and good luck with the wonderful summit and with continue of your studies.
Thank you, Professor Pistikopoulos and Professor Reklaitis.
Very good.
Bye-bye.
Sweet.
I would like to thank Professor Pistikopoulos and Professor Reklaitis for taking their time to organize the panel for us and provide informative insight in process optimization with various industrial applications. Our last talk for the day will be presented by Professor Peter Halley. Peter Halley is a professor in chemical engineering at the University of Queensland. From 2014 to 2019, he was also the head of school of UQ Chemical Engineering. Professor Halley works in polymer engineering and processing research at the translational research interface between university and the industry. Specifically, his research involves rheology, processing, and product design of biopolymers and nanocomposite materials for agri-food, biomedical, and high-value manufacturing sectors. He has worked in the industry, cooperative research centers, and has acquired and managed continuous government and industry research projects since 1994, and was heavily involved in the spin-off of Quantic Technology. I would like to call Professor Halley, who will now talk about sustainable biopolymers in the plastics economy.
Okay, excellent. Can you hear me all? Okay. hopefully. I've just got to work out how to run my slides. Okay, so if you can hear me, I'll just move on to the first slide. So I was just asked to put in a little bit of information about an example of one of our research projects that ended up in a startup company. This talk is about sustainable biopolymers as part of the circular plastics economy solution, I guess. And this gives an example of research that was done basically from test tube all the way through to final products. So yeah, I'm, as it says, Peter Halley. I'm from the polymer group at UQ Chemical Engineering. We're called the TPRG, Translational Polymer Research Group, which is all about translation from, can't work out which way my hands go, from translation from lab through to final product. So it's probably all about the chemical engineering of polymers. So let's move the slide. So I'll just go through some basics on the circular plastics. I think this will be, or circular economy and circular plastics will be a big area for you guys when you graduate. So I'll give a bit of basics of that, talk a little bit about the plastics part of that circular economy, and then a bit of the case study information about the startup company Plantech Technologies that came out of our research. So yes, our TPRG is spread over many buildings here at UQ, but essentially it just basically goes from polymer chemistry through to polymer processing and chemical engineering through to modest size scale up processing at our UQ Long Pocket labs. So industry come in sometimes to do what they call small, we call large batches of extrusion or film blowing out at Long Pocket. So as I say, we're a very translational group, I suppose. Why would we want to look at sustainability now? Well, we live on a big spaceship and we need to live sustainably, and as yet, there's been no other spaceships for us. So that's very simply why we need to be careful about what resources we're using. In terms of plastics, over the years, since the 70s, we've seen basically a 20 times increase in plastics being produced, but unfortunately, only about 9% of it is recycled. There's many of these types of figures, but this is one that Professor Bronwyn Laycock has been researching here at UQ. So you can sort of see down here of the entire green bar of, say, total production, roughly only this 9% of materials recycled. Other waste is either incinerated, but by far most of the plastic waste gets landfilled or actually is called leakage, is littered. And of course, we know that this has problems with plastics entering the ocean, either as microplastics or as plastics waste itself. So we have to do something about our use of plastic, and that use means we don't throw everything away, because some plastics are very important. They stop food waste, for example. They are protective. Some are high performance plastics that reduce weight in vehicles and therefore increase fuel efficiency. But we want to make sure that we value the plastic all the way through to its end of life. And in fact, we want to generate new markets for plastics. So one of the first people to look at this was the Macarthur Foundation. I don't know if you know, Ellen MacArthur was, I think, a British Olympian who was known for long sailing trips. I think might have been the first one to sail around the world in a very small boat. But on that trip, she often said that she saw a lot of plastic waste when she went around the world. So has established this foundation, and the foundation is now well known in terms of circular economy and circular plastics. She's basically said there's three things we need to look at for the circular plastics economy. They're written up there. They're also on this diagram too. So firstly, she wants us to look at an after-use plastics economy. Normally when virgin plastic is used, it's just either, as we saw, only 9% of it's recycled. We want to increase that amount of recycling by making other uses for plastic waste. In fact, she doesn't want us to use plastic waste term. We want to just keep saying plastic is a resource that is wasted at the moment, and we want to make sure that resource is recycled and reused. And also, this also will mean stopping leakage of plastic into the environment, like with marine litter and even any litter, actually, and also decoupling the use of plastics from traditional fossil feedstocks and maybe looking at biosources. And that's probably where our research comes in. So yes, our research, traditionally, plastics are usually produced and then perhaps either recycled for reuse, or you can actually look at chemical recycling or mechanical recycling of plastics, or even returned to original materials and then reprocessed. But what we're talking about also here, I suppose, is this additional bio area. So what if we started to also get bio sources for polymers and plastics, and we're able to then either recycle them, either back into, well, through anaerobic digestion, back into biogas, back into use as a biochemical feedstock for further plastics. So I guess that's what this talk is about, is the bio part of the circular plastics idea. Many people have probably seen the different ways of what happens to plastic waste. A lot of it's happening at the bottom, but we can push upwards and try and look at other options for plastic waste. It has the same calorific value as fuel. So why are we not trying to retain energy at the very least from plastic waste? Can we recycle? Can we compost? Can we reuse it? Can we reduce its need to be used in the first place? Dow Plastics at the moment have huge research going on about replacing the 7-layer, multi-layer film made of essentially different types of plastics with just one layer and maybe some clever nanomaterials inside that achieve the same type of barrier properties as the multi-layer film would, and therefore the single-layer film will be easier to recycle. So anyway, there's different ways of trying to stop plastic waste. Here at UQ, we are looking at each of the different areas. I'll talk today about sustainable feedstocks and biofeedstocks, but of course we can focus on other things, clean chemical synthesis, the actual optimization of your polymer processing itself can be a sustainable polymer area. And even avoiding the waste in the first place, or creating some new biodegradable materials that are able to be composted and recycled in the broadest sense. So we've established an approach here at UQ. There's a new UQ Plastics website. Hooray. Just Google UQ Plastics website if you want to see. But essentially we're trying to examine the entire supply chain and including information like social sciences, like consumer behavior, like policy from government, end-of-life management. Do we need more waste conversion facilities in Australia? We probably do. We're missing data. Do we know where plastic goes from? The other day, one of the NGOs who's looking after the barrier reef and plastics in the barrier reef said, did I know that 90% of plastics north of Cairns on the beaches come from overseas? No, I didn't know that. But I guess with lack of people north of Cairns, it's probably where the plastics is coming from. But that's an example of data based on, or actually getting some data and trying to understand where the waste comes from before you can solve the problem. Sounds simple, but some people are trying to throw solutions at problems at the moment without actually understanding where the problem is. And I guess that it's the same thing in a different diagram. So we're trying to introduce human factors and data, cycles and impacts, to our technology that we've been working on for many years at UQ to hopefully have this integrated solution. Andrew Liveris today just gave a talk on Zoom at UQ, and he kept talking about the power of and the tyranny of or. So look for a solution that is a technological solution and people will use it, or people will understand how to use that technology, or do a technology that it actually focuses on the area of waste that you know to be the true cause of that particular use of that plastic. And of course, the foundation is, of course, undergraduate courses. We're trying to develop PhDs, masters, etc., in the whole of this integrated solution to circular plastics. This is probably too much information. So anyway, let's just say this UQ Polymers or UQ Plastics Centre now has a number of people around the university on different areas, as you'd imagine, from production, consumption and manufacturing in this three-tiered approach of technological, social and political or policy solutions. That brings me to the case study. So I just wanted to show a couple of slides on our, 20-year history of developing bio-based plastics. This started in, 1995 with the Cooperative Research Centre of Food Packaging. It involved us, so CSIRO Melbourne, Swinburne University in Melbourne. Just basically, it was the best project ever. Here, guys, you design a totally new type of plastic based on starch. Oh, great. Okay. Anyway, but it allowed us a lot of freedom, and there was a lot of industry partners like Goodman Fielder with the starch supply, ACI Packaging were people that wanted bio-based packaging, but they allowed us to examine all sorts of different plastics products for 7 years. So essentially, then Plantech was formed, startup company. Plantech, the name comes from obviously plant or plastics from plant. That was formed, and then the good thing, I guess, is that we were helping them as first contracted researchers, then as through linkage grants and PhD students in developing their entire new product line. So there was, I'll show you soon what products were made, but this was a really exciting bit because the students, so this is undergraduate students doing thesis projects, PhDs doing PhD projects, and overseas students coming for like 6 months placements who in turn stayed to do PhDs, all developing new products for a startup company that was essentially formed out of the ideas of the CRC's PhDs. So it was a really cyclic type of nice story, I guess. Really only stopped 2018 when Plantech eventually got bought by a Japanese barrier company called Kurore. But now we're engaged with them again to try and keep on going and develop new research for new starch-based products. So this was an exciting time, we thought, but as you see, a long time, 23 years or so of doing research. And note that the products didn't come out until around about 7-8 years of initial research. Why were we successful? We thought it was because we were based on low cost or cost competitive biodegradable plastics. They used conventional equipment, didn't need special equipment. They were not over-engineered. A lot of people don't know these standards. These standards are ASTM standards that actually talk about the actual specification for, say, a garbage bag. Polyethylene is probably 5 times over-engineered for a garbage bag use. No one knows that unless you look at this standard and say, oh, you only have to meet about 1/5 of that standard. Okay, we can do that with our starch-based plastics. Anyway, that was, so not over-engineering properties was the second point, and then using some clever technology that came up through the work, through nanocomposites, through blends, through multi-layer materials. And so what came out? Well, first to come out was starch mulch films. I think we were the first in the world to blow these very thin black mulch films that's used for greenhouse films for tomato crops, capsicum crops, stops weed growth, allows even temperatures underneath your crops, helps retain moisture in the soil so you don't use as much water. So we got really good trials that were scaled up, and I think that was the first type of product that Plantech had. The first product they sold, though, was the other work we were doing on injection molded cups. This is actually an OV trap or a mosquito cup that's used to control dengue fever in cans, if anyone's been all across the world. But specifically, we were working with cans. You basically, if you have an outbreak of dengue, you put these cups around, the red cloth has insecticide on it, and put water in there and you'll attract the dengue mosquitoes who will breed, but will be breeding on insecticide, and then eggs will die. However, the insecticide only lasts 6 weeks, so then of course you've got an excellent bucket to increase the amount of dengue fever that you have. So people from Queensland Health have to go and get the buckets. They wanted us to design a bucket that would fail and the water would release at the same time as the insecticide would wear out, and therefore the mosquitoes wouldn't come back because they're not attracted by, dengue fever mosquitoes are only lay eggs in very still water. So this is why they were using these. But anyway, yeah, we were able to produce a cup that failed at the right time. And so this was our first product from Plantech. The next product people might have seen more about is the chocolate dairy milk trays and Arnott's biscuit trays. It was made by water-soluble starch-based materials. They also used it in the Easter egg display eggs as well. But then they got stuck, that they had only got products that were water-soluble. So we then did many years of these linkage grants, ARC linkage grants with PhDs, working on further understanding what was really happening with the interaction of the starch polymer with the environment. So we looked at properties, degradation as a function of environment. We looked at model starch systems. Can we actually grow starches or genetically modify them to be have better properties for films? And what is going on with the extrusion? Are we degrading the starch while we're extruding them at these various conditions? So hopefully this would lead Plantech to new types of products. And what happened? Oh, we came up with a better way to produce very, very thin Plantech films. So these were aimed for barrier property films. That was a great idea. That came from understanding flow through the dye a little better. This is an unusual shaped dye. It's not a polyethylene shaped dye. It's actually a starch shaped dye because we don't want to have sort of rectangular or 90-degree angles, because that's where starch degrades quite a lot. So we want this nicely shaped dye so there's no spots where the starch can sit and degrade, basically. But we then examined the barrier properties. It looks like starch when it's in between a multi-layer of PET, and starch. Starch has excellent oxygen and water vapor properties, barrier properties, sorry. So we actually found that out by doing a range of tests on different types of multi-layer films. And then Plantech launched the meat trays in Coles back in, I can't remember, maybe 2013, maybe? No, that doesn't sound right. Anyway, after, 2012, there. So they'd made both the film on top of the tray and the meat tray itself from Plantech material because it had good barrier properties in this multi-layer format. And what did I learn? I learned that this was fun. This whole idea of doing research at a university, but also engaging with a cooperative research centre with many people around Australia, and then the PhDs who worked in the CRC and then subsequently with the startup company got fantastic experience. So imagine getting a PhD and an exciting startup company experience at the same time. It was a bit dodgy at times with the cash flow not coming into the startup company. However, University of Queensland and CRC backed us, essentially, backing the entire scholarship of the PhDs so that they would never be left high and dry. And also there was an engagement of the honours students and the vacation students from overseas, and it was excellent. An excellent sort of, we had at one stage, postdocs supervising PhDs and who were supervising overseas students, and so everyone was getting supervision experience as well. So that was a few learnings from that experience. Where we're up to now? Well, it's a busy diagram, but essentially, where's that work? That works probably somewhere here in the smart materials of starch. When I became head of school, I stepped aside, and two others in our group, Paul Luckman and Bronwyn Laycock, got great research going, and probably I got out of their way, so that was really good for them. No, anyway, so I'm joining them again after being head of school, and we're going to look at what they've built up. So they've built up, as you can see, things from biochemicals, from polyhydroxyalkanoates, PHA polymers that are produced in wastewater treatment plants as the energy source for some of the cells there. Lignin from wood or sugarcane, biocomposite fibers, use in fertilizers, for high performance of biocomposite materials. So there's a whole range now of these technical projects that we hope to match up with others in the circular plastics area, like social scientists and policy developers and industry, to be able to offer bio-based materials as one of the solutions, I guess, for some products that help make the circular plastics economy grow. And that's probably just saying what I just said. Anyway, we think that this is a great big area inside the circular economy in the area of plastics. Obviously, other materials for batteries, carbon itself, I think, are other materials that should be looked at very closely in this new circular economy as well. And we'll be looking at other projects involved in marine plastics, in collecting data, where that's coming from, and also our old traditional area of high value added polymer materials design and manufacturing. And maybe we can start designing materials for recycling and reuse from the very, very start, instead of waiting until we get to the end and worry about recycling them. I think that might have been all I have here. So yeah, it just leaves me to thank all of these funding agencies in our big trip. Actually, there should be since 1998. It's not that long. Anyway, 1998, but it's still a long time. And thank you for listening. And I can take any of your questions.
Thank you, Peter. I see we've got a few questions for you. The first one's from Azriel. Is your research more centered around technical aspects of biopolymers or the human aspects?
Very much technical. So we've had a lot of work. I guess I started on traditional plastics, so as polyethylene films. I moved into thermoset plastics, so sort of computer chip integrated circuit packaging, thermoset materials, and then we had that start of that biodegradable plastics work inside the food packaging CRC. So, but yes, you're right. Everything was pretty technical. I guess you could say we switched from starch to be used as packaging film and industrial films over to starch for industrial products in the last 5 to 10 years. So now we look at starch used as a depressant for flotation of minerals, for example, or starch to be used as a coating for fertilizer to deliver the right amount of fertilizer to crops up in North Queensland, so that they don't have too much fertilizer going into the Great Barrier Reef and causing algal blooms and cutting off photosynthesis, etc., etc. So yeah, I think it's always been technical. Probably while I was head of school, Bronwyn has been the one that my colleague who started the work, she started to engage with Queensland government on their new plastic ban policies, and also engaged with social scientists here. She did a big survey of what is Australia's view on plastics, and then the second survey was what is Australia's view on bioplastics. And so she's been the one that's starting to move outside, I guess, the technical area.
That's very interesting.
Yeah.
And so there's a question from Samson. There was a young European guy who set up a project to help clean up plastic waste in the ocean using gyres or something a couple of years ago. Can you point out towards any promising studies or projects which have been used to convert plastics to oil?
Yeah, sure. In fact, well, actually, we're involved in one at the moment. There's a company called Lysella in New South Wales. They're actually looking at waste to oils in general, and we're actually looking at a range of different additional products to be added. So I guess when you're taking waste and converting it into oil, you might be restricted by the type of waste that you're collecting from wherever you're collecting it. So they've decided, okay, that's great. They've got their company started up. I think they've got a large plant almost ready to run in UK as well. I don't know why it's not in Australia, but anyway, it's in the UK. But they just want to know, okay, can we make a better grade of fuel? Can we make a fuel that's going to burn better or have less emission? Or so they've now engaged us to say, okay, rather than just take any waste, what other things can we put, or what other bio-based materials maybe could we mix with the waste that we get, so that we can then have more of a controlled input and then obviously a controlled output of fuel. So yeah, that's an example. I guess Lysella is an interesting company, a startup in Australia But yeah, there's many different types of solutions, and at the moment I'm a little worried that people are rushing off with as I say, the solution is leading the understanding of the problem. So there's often that big paper gets quoted a lot. I think I'll have to find out who it was again, but there was a paper talking about how much of marine plastics is in the oceans, and it's reported to say, I think it's 8 rivers in the world contribute over 80% or 90% toward the waste, and these 8 rivers are, have common characteristics of 1 million people in the river. They're really long rivers. They don't have any waste collection in the towns or the small villages along the river. So it's obviously that marine waste problem may be revolving around getting better waste collection along these 8 big rivers first, and then worry about other types of solutions like bioplastic, for example, if you want to solve the ocean plastics problem.
Thank you. We have another question by Nithya. What type of nanomaterials would be used in a single layer plastic instead of the 7-layer plastic? And how is this embedded into the plastic?
That's a good question, and of course Dale won't tell me. So, but if I was a guessing guy, which I am, because we added like clays, organic clays, and then modified clays. But you're not. Yeah, it's tricky, isn't it? When you add these nanomaterials, you're adding at the nano level, but you're actually affecting the macroscopic or the crystallinity of the material and the larger level structures, I guess. So I'd say they're probably doing something similar. They're probably going to be looking at some nanomaterials, but the nanomaterials are not there just for their own sake, or they don't increase the barrier property, but they'll probably be affecting the crystallinity or the larger scale structure inside the polymer, and that will then affect the increased barrier properties. It would be my guess.
All right. Another question by Romalia. Given the changing societal mindsets is pretty challenging, how does this affect your field of work, and how do you go about it?
Sorry, I missed the first bit.
Given the changing societal mindsets is pretty challenging.
Yeah, no, you're quite right. And in fact, one of my old postdocs who's now over at Warwick University wrote a paper, I believe, on the increased use of plastics in COVID. Obviously gloves but also the fact that people don't want anything to do with them and just throw them out, and they're not either thinking about recycling or not even thinking about because everyone's scared of this. My gloves have COVID. So anyway, that's an interesting piece. But yeah, things have changed. Well, interesting. Bronwyn surveys was interesting. Bronwyn, who sent out, what do people think about plastics and bioplastics? The bioplastic one's easy. They don't really know, because we haven't done a good job of saying, what does that actually mean? Does it mean bio-based materials are used in the plastic? Does it mean biodegradable plastic? Does it mean so we haven't actually defined it, so that wasn't surprising, I suppose, that survey response. But the plastic survey response was interesting. So basically everyone was really keen on doing something to stop plastic waste or to reduce it, but they all wanted to push it to the industry. Industry's got to come up and pick up my plastic bag, or don't design it this way. But I think as Andrew Liveris was saying with his quote about the goodness of and, I think, but the tyranny of or. So if you come together to try and do the solution, industry can design plastics that are better, easy to recycle. Users can be better at actually finding a bin and not leaving it on the beach or something. And also, the processes themselves, the industrial processes, can be better about catching waste before it goes to drains or something like this in the plastic pellet making process. So I think everybody has to make a conscious effort. There was a really interesting survey that everyone wanted to do something about plastic waste, but when it came to them doing something, no, I don't want to do that. I don't want to have 3 bins. That's too confusing. No, but that was a joke. But I think that we'll have to learn to each take a share of the responsibility. It's sort of like the energy. The energy solution won't be all solar, won't be all dams, won't be all gas. It'll be a mix, and the mix will depend on the area. I predict, the same sort of distributed solution will occur around the world for plastics, depending on your type of use of plastic.
Okay. Due to time constraints, I guess we'll shorten it now. So thank you very much, Peter.
That's okay. Cheers.
I believe there's some issue. Sorry, just I think I'll just take over to end. Thank everyone for attending today's session. Just overviewing, we had 4 speakers. We had Fabio Silveira, Professor Pistikopoulos, Professor Reklaitis, and Professor Halley talking on sustainability. Please note that we are having a trivia session happening tonight from 6 to 8 p.m. AEST. And tomorrow's session will be happening over biotechnology and pharmaceutical with technical talks in the stream 1 panel and panel session in the stream 2. And we will also have the networking session on Friday evening after the closing session. Thank you everyone for attending, and I hope you have a good day.